Okay, looks like it's recording. I tried to wait for the birds to be quiet, but it seems like they're just on a roll this morning. So excuse me for the extra noise, but I'm trying to talk into the microphone. And today's the topics that I want to talk about in the videos, divided them up into a couple of different videos, so each one won't be as long. And the first one is capacitance, but just a quick review before we do that. What we were talking about is we were talking about the capacitance you see on transistors, and we saw a picture of the MOSFET. It had capacitance from the source to drain to substrate. Had gate channel, and remember the gate channel changes depending on what region of operation you're in. And then had the overlap capacitances. Those are called physical. So these first two are called diffusion capacitance. These are physical, and this is the gate channel capacitance. And those were the capacitance for a MOSFET. And if you drew them in on the actual small signal model, what you got was, if you look back over here, you have a source to substrate, source bulk. So you had actually one, you had a source bulk, and it had a drain bulk. And remember, the substrate is at a DC value, so that becomes an AC ground. And then you have these overlap capacitance, which is gate source and gate drain. So you have C gate source overlap and a C gate drain overlap. And then the last capacitance is from the gate to the channel, and we're in the forward active region, so that's going to show up also as gate source capacitance, which is this right here. And remember, it's coupling two electrons in the channel, but since the channel, those electrons are kind of leaning towards the source, that's considered gate source capacitance. And this right here we don't see because we are working in the forward active region where there is no drain, gate drain overlap. Oh, this says DD. Oh, this should be CG. That's supposed to be G. You have the drain bulk. You have the gate bulk. That's also, we don't see that because that's what we see in cutoff. This is what we see. We see this if we're in linear. We see this if we're in cutoff, but we're in active, so we get to ignore those. Okay, and then see if we can find for the BJT. Where's the BJT? Where's the BJT? Where's the BJT? Okay, and then there's the BJT capacitance. And everywhere there's a boundary between the P and an N region, you get a capacitance. Okay. And for that one, when you draw those capacitances into the small signal model, you see you have a base emitter capacitance. So you have, oops, it says gate. That's base. Wow, okay, we got all MOSFET models here. So let's make this into a BJT model. All better. This goes away. So here's the emitter. That's the collector. Okay, so you see you have a base emitter capacitance. So what you have here is base to emitter, and I'm fine with you calling that CBE, but the official name that you'll see in a lot of textbooks is CPi, because it's in parallel with RPi. So this is CBE right here, or CBE. Not sure if you can read that. Okay, and then you also have a base collector capacitance. So there's base connecting the base and collector, and that's often called CMU, but I'm fine with you calling it CBC in this class. And then you have another one, collector to substrate, and again the substrate is a DC value, so collector to substrate, and that's where you get the capacitances from the transistors. And when you take 431, you'll see that every wire that you draw, that you let's say you connect two transistors together, that wire is also contributes capacitance. And I'm really sorry about the birds. I was hoping they would be quiet, but hopefully I'm overpowering them. Okay, so that's where the capacitance on the from the transistors come from. And the reason we care about that capacitance is that it combines with any resistance in your circuit and makes either a low-pass circuit or a high-pass circuit. So hopefully it's not too far in the future that you know that this is a high-pass filter. This is V out, V in. And then if you switch the capacitor and the resistor, then you get a low-pass filter. Okay, so you've seen that before. All right, so it's just to, because so much of this class is about, well, for me, is getting used to kind of having a feel for circuits. Let's understand why a low-pass filter, low-pass filters, and why a high-pass filter, high-pass filters. We've got all these different R's and C's, and Barkhausens, we'll talk about that when we get to feedback, but it is a frequency response topic. And as mentioned, every circuit, every time you draw a wire, every time you use a transistor, you have capacitance. Turns out every wire has resistance, every transistor has resistance. So even if you have no intention of putting R's and C's in your circuit, you end up with R's and C's in your circuit. Inductance, same thing, except inductance doesn't tend to be a problem until you get up to really high frequencies. So when you get up to some of the RF classes and things like that, you'll see that all the details of that. Okay, and to get around inductance, we say, hey, we're going to look at medium frequency response. And that just means pretty much that you get to ignore the inductance. And even more hand-wavy, I shouldn't say hand-wavy on this, but because these capacitances, when you work out the capacitances, say that the gate channel capacitance or the gate source capacitance for a MOSFET, you see that it is so small that any pole or zero that it causes is way out in a really high frequency. And because our equipment isn't good enough to see the actual poles and zeros, what we're going to do is we're going to add two capacitors to our designs in lab. I'm talking about lab right now. Because the actual R's and C's are so small that they give us a really high pole, a really high zero that we can't observe because our equipment can't see that high a frequency. We are going to add two capacitors to make our intention are poles. But if you're using an AC coupling cap, you'll also see a zero in there. But anyways, we are going to add capacitors to create poles. so we can observe them. Just because our equipment can't see the poles, can't see the frequencies of the poles that actually just naturally exist, we are going to artificially create poles by adding capacitors to our amplifier. I think I've said that enough time. Okay. Just generally, what a filter does is, if, let's say, this is a low-pass filter. So for a low-pass filter, if something this is the time domain, if this is a sine wave you see and it's kind of slow, it generally passes with the same amplitude through. But if you speed it up, this is still letting the amplitude through. But at some point, you're going to get to a frequency where the amplitude doesn't get through. The amplitude is reduced. And you say, well, you know, how many in a circuit does that really show up that much? And I'm not giving you a great lead into this, but what I'm trying to say is that, you know, that the R's and C's, I mentioned the R's and C's occur every place. And I just took this and I circled all the places where I saw some R and C. In other words, something that's going to make up either a low-pass filter or a high-pass filter, and came up with that. So, yeah, it's all over the place. But if you're analyzing your circuit, you don't want to have to analyze all of these. So what you want to do is, in general, you find where the signal's coming through coming in, and you follow the signal path. So here's the signal path, goes over here, over to here. Yeah, you want to follow that signal path. And this is a 555. Oh, I wrote it up there. 555 timer. But yeah, you follow the signal path. If there's capacitance on a supply, that's great because it quiets the supply. That's not a problem. But if it's in the signal path where you're trying to get something to move and it's changing the amplitude of that signal, then you have to pay attention to it. Okay. Yeah, sure, why not? Okay. So I think, actually, because this is going longer than I thought it would, we're going to add a topic. And the first one is just filtering. So we're getting there. So what is a low pass filter? And low pass filter, again, it lets low frequency signals through pretty much as is, but as soon as you bring the frequency up, it starts to kill the amplitude. Okay, so the amplitude drops. So let's look at this. There's a rule of thumb that I encountered in some textbook and talking to some people from industry, and they said, yeah, if you have about a period of about 10 RC, then you consider the voltage that your output signal. So this is your input signal. This is your input signal. Here's your output signal. If you are doing 5 RC, greater than 5 RC right here, you can consider this voltage basically as reaching its complete max voltage. In other words, this voltage and this voltage are the same in a filter. And same thing with a drop. If you have 5 RC, you generally consider that as having reached, having this voltage equal to this voltage. So they generally reach the same voltage as the input. Okay, it's not 100% true, but it's close enough. Okay, so let's see if you, so the period's greater than 10 RC. Let's see, if you make it smaller, now this starts to charge up, but it doesn't quite get to this maximum voltage. It doesn't quite get there, and then it tries to drop. In this picture, it looks like it drops all the way down to 0, but it tries to drop, and it doesn't quite get down to there. And then all of a sudden, you're telling it to go back up again before it's gotten all the way down to the bottom. So what's happening here is you're telling it to go high, but it doesn't quite get to high enough before you start to tell it to go down. And then before it gets all the way down, you're telling it to go high again. So it doesn't quite reach the maximums and minimums that you got with having a 10 RC period. Okay, you keep doing that, and when you get up to a high enough frequency, you get this. And if you look at what's happening to the capacitor, when you look at the filter, what you're seeing is that you're not giving the capacitor time to discharge and charge. Okay, so I'll say that again. All a low-pass filter is a circuit that doesn't let the capacitor completely charge and discharge. When you run it slowly, it has time to charge and discharge, but when you run it fast enough, it doesn't have time to charge and discharge completely. Okay, and that's what's happening here. You tell it to go high, but you don't give it time enough to get to that high voltage, and then you tell it to go low. And you're like, oh, I got to go high. Oops. Well, now they're telling me to go low. Oh, now they're telling me to go high. So basically, again, all a low-pass filter is a circuit that doesn't let the capacitor charge and discharge completely. Okay, and you can do the math, and I'm sure you have hopefully in 211. Yeah, this should look familiar. Okay, so what's a high-pass filter then? Right, so what happens with the capacitor is if you change the voltage on one side, the other side has to change with it. Okay? The voltage across a capacitor cannot change instantaneously. So if you change the voltage on this side also has to change with it. So if you raise this side also has to go up. But then after it goes up, now it discharges through the resistor. Okay. And again, you've got that 5RC rule. Works for this too. It says that if you wait 5 RC, let's say you raise this, you raise V in, by 5 RC it will be back down to 0 over here. And the same thing here. If you drop this, then immediately V out drops. But then if you give it 5 RC, it'll go back to 0. Okay. 5 RC, 5 RC, 10 RC. But let's see what happens if you don't give this node time to discharge through the resistor. Okay, remember, low-pass filter is you're not giving a capacitor time to charge and discharge. With a high-pass filter, the faster you go, the output gets more and more like your input. And what you're actually doing here is now you're not giving this node time to discharge through the resistor. So a high-pass filter is basically you change the voltage at this node, but then you don't give it time to discharge. Oh, actually I should have said for the, okay, I take that back. Not charge and discharge for the low-pass filter. My bad. What you see is that you're not giving the capacitor time to charge for a low-pass filter, and for a high-pass filter you're not giving this capacitance time to discharge. I will ask a question specifically about that so people can, instead of re-recording this, I'm going to ask a question on the homework about this then. Okay, so low-pass filter, you're not giving it time, the capacitor time to charge. For high-pass filter, you're not giving the capacitor time to discharge. Okay, so that's basically what the filters are, and there's a number of symbols out there. I generally use these right here, but you'll see some others. And various kinds of filters. When you intentionally plan for a filter, you can have a low pass, a high pass, a band pass, or a band gap. This is often used to get rid of 60 hertz noise, where you just have that one place, that 60 hertz, where you don't let that 60 hertz through, but all the other surrounding frequencies you let through. Okay, and this is for a radio. When you turn on to a particular station, it needs to get a particular frequency, so this just picks out that particular frequency. High-pass filter, there's a number of reasons for this. I'm not thinking of a good example right here. Low-pass filter, noise, there's two types of noise that are most common. One's a high-frequency noise, and one's a 60 hertz noise. So you can get rid of the 60 hertz noise with this, but this right here, if you cut out the high frequencies, you get rid of a lot of noise. Okay. And as you did in a bunch of other classes, I'm sure, is when you plot these frequency response, which is basically the amplitude versus the frequency for the magnitude, which is what we've been talking about, you use a Bode plot. And so I have a number of slides here talking about Bode plots, and I'm 100% happy to work through these with you, but the main thing that I want you to know is that for a Bode plot, well, I have 0 dB here, so this is still for a filter. I mentioned in class that for amplifier this will not be 0 dB. Okay. That at this pole right here, it's 1 over RC, and that's if you're in the omega realm. If you're in the frequency realm, then you have to multiply the RC by 2 pi. Okay, so if you're in the Hertz realm, you need to multiply the RC by 2 pi, and it's 1 over 2 pi RC. Okay, and then when you get over here, now you've got your minus 20 dB per decade. And if you have another pole, it just adds, and now you have 40 dB per decade. So that's really what you need to have for Bode plots. And I'm totally happy to set up another session and meet and talk about this if there's a group of people that are interested. Okay, and phase response, phase response is just how much the output signal is shifted from the input signal. Okay. And oh yes, this is pretty important too, especially when we get to feedback. So at a pole, what you get is whatever this frequency is, you divide it by 10, and that's where the phase starts to change. So whatever this frequency is, let's say call this F1. This is F1. This is F1 over 10 right here, where the phase starts to drop. At 1 over RC, it's dropped by 45 degrees. And then at 10 F1, that's where it's gone. That's where it's dropped the full 90 degrees. And then at the next pole, again, if this is F2, then this is F2 over 10, and this is 10 F2. Anybody that needs kind of a summary here, I forgot to check this, but just kind of a summary of how poles and zeros affect your the Bode plot, or the frequency response. Basically, the Bode plot is the frequency response. Okay, we've got some practice stuff here, some reference sites, and that's all. Okay, so I guess the first segment here was on filters, and the next will be on capacitance.